Hey everybody, and welcome back to Linear Algebra Online. So I just want to start off with another one of these is this thing a linear transformation kind of problem. So sometimes we also write them this way, and if you look at it, so x is like an arbitrary vector, so it's a linear transformation of that vector, and you get this thing. You have to kind of look here to see how many what dimension your domain is. And you can see there's only x1 and 2. So that means that we're sending R2 to, there's, 2 commas in here. So there's 3 things in here. So we're sending it to R3. So when I write this x here, I'm basically talking about x1, x2. So I'm going to start off with like the scalar property. So L of like C times x or something is basically the matrix cx1, cx2, and then x1 plus 2 cx2, right? And then I could factor a c out of all those, right? And I get x1, x2, x1 plus 2x2 transpose. And that truly is c times the linear transformation of x. So that basically proves that scalars can pass through this operator. And so we're good with that. And then for the addition part of the linear transformation, L of u plus v would look like this. And then I might actually switch to columns because I think there's space. So then I can group, basically multiply in group-like terms. I could get u1, u2, and then u1 plus 2u2. And then I could do plus v1, v2, v1 plus 2v2. And if you look at it, right, that is, that's good. So that is the linear transformation of u plus the linear transformation of v. And so, that really does prove that this thing is a linear transformation. All right. So let's say that I just want to kind of go back to this little matrix that we built up last time and say something really important about standard matrices as well. So this was the matrix that we get for some arbitrary line L through the origin that has direction vector d1, d2. And this sort of formula is basically a projection onto that line. And so you could take this, right, and you could take lines like y equals 0 would be the vector 1, 0. Y equals x would be, we'll do some colors here. Y equals x would just be like a vector 1, 1. Y equals 2x would be a vector 1, negative 2. And lastly, 3/4 of x you could write as 4, 3. Then you could take these x, d1, d2, right? And you can pop them in here, and you would get these corresponding matrices. All right. So you get all those. So this one, corresponds to this to this, this to this, and this to this. And so these are what we call standard matrices of projection for these different lines, okay? The really important result that I want you to know is that in linear algebra, if there exists a standard matrix, then it is linear, all right? So all things that you can represent as a matrix are inherently linear transformations, which is really important property. So a lot of what we do on the higher level of math is try to construct some sort of matrix And sometimes them things don't work that way, and they are just nonlinear transformations. But if we can construct this matrix, then we've inherently also proven that that transformation is linear. And that's really nice. It's going to do things like keep the origin fixed in its spot. It's going to like keep the grid lines like spaced out evenly, even though they might be kind of warped and twisted or whatever. But they're going to be like straight-ish. They might not all be orthogonal anymore, but they're going to be evenly spaced, which is important. So that's a very important result that I wanted you to see. And I thought I'd also show you this. So I just went and I popped in a few things to show you that this matrix, which is the 3/4 x projection one, really does do what we said it should. So this is the vector -1, 3 right here. And if we apply this matrix to this vector, we get this in the range. And this vector is right there, okay? And you really can see that this thing is like projecting down. That really is like perpendicular right there. But it works. This matrix times this projects any vector at all onto this green line somewhere, which is that line drawn down there. Just thought you might want to see it. All right. Just a few more little things here. So there is kind of a formal definition of composition of linear transformations. And I'll just kind of read it off to you here. So if you have a transformation that takes like Rn to Rm, and then another one that goes M to P, those are linear transformations. Then the composition is denoted this way. It's the same notation as always. And it's a function that now goes N, right, over to P. And we write it like this, right? So we always put the first things on the right. Actually, the reason this composition notation is backwards, and that confuses tons of Algebra 2 students, is really because of how matrix algebra works. So they stole this notation. No, they created this notation and steal it, but they stole the order from matrix multiplication notation, which was around before, actually. So anyways, this is understood, right, as T acting first on X, and then S acting on T, right? And this kind of gives you an idea of why like domains and codomains need to align so nicely. So, the codomain of T and the domain of S must match. Like when we do matrix multiplication, if this 3 is how it ends, this has to be a 3 in the beginning, and then you're going to get a 2x5 matrix there. And this is like the standard picture that you should think of, like this vector, this thing maps to here, and then it takes all of things in Rm now, S does, and this is in there. This is in the range inside of the codomain of T, and maps it over here. Really what I want to show you with this is, if we use this idea of composition, we use this a lot of times to do these kind of things. So I'm just going to run through basically a kind of set up one of these composition problems, and really just want to hammer home like the order of how we need to put this in. So if first a matrix does a projection onto line y equals x, the line y equals x is could be represented as like 1, 1. So if I go back here, it was purple over here, but this is like the first matrix that you need to have. So I'm just going to copy it over from there, 1/2, 1/2, 1/2, 1/2, right? And then if we follow that by a projection onto the y-axis, right? The y-axis projection is, projection onto y-axis would be -1, 0, 0, 1. Right? That's not, sorry, that is the, that's the flip one. The projection one, we need to kill the x component, right? So that's the projection onto the y-axis. And then I say follow this up by a rotation. I have a typo, my gosh. Counterclockwise by 8,297 degrees, because why not? So here, I'm just going to put in, we basically have this we have a cosine, negative sine, sine, cosine matrix. And the negative up here would be the counterclockwise rotation one. So we'll have cosine of, I'm just going to say define theta as 8297, right? Cosine theta, and then negative sine theta, and then sine theta, and then cosine theta. So this is, again, like how you have to do compositions in linear algebra. You start over here, just like you start over there, and you work to the left. You work to the left. I'm not going to go through all the multiplication here. This is messy anyways, but the standard matrix would literally be this stuff all just multiplied, and you really can just combine it. And since you can get one matrix there, that means this thing is a linear transformation. Basically, that doing all those weird things back to back to back is some sort of thing that's going to keep like the origin fixed, and it's going to keep grid lines like evenly spaced apart. And to calculate this thing out, you do this times this first, which is pretty nice because you get some A-zeros. And then you multiply that result by this, and you just have some crazy numbers, probably like, I don't even know. It's going to be some decimal below 1 and above -1. But that's kind of the idea. And I want to just show one last thing here, where we could kind of think of doing this with this kind of structure where you have the linear transformations sort of written out in general. And so really to do composition here, what I would do is I would just get the standard matrix that represents each of these. So like for T, this is kind of the normal notation. You put like a little box around T. Its transformation, since you have like two variables in here, right? Two variables here. You know that you're going to have an X and a Y column. So you're going to have something, the first column needs to be all the X stuff. So 1, 2, 3. So we'd have 1, 2, 3. And then the Y stuff, there's no Y in the first one, and then -1, and then 4. So that's like the standard matrix for T. And then likewise, the standard matrix for S. So here you can see we're going to need 3 columns, a Y1, a Y2, and a Y3. And we would get 2, 0, 1, 0, 3, -1. And I don't think I have enough room. And then 1, -1, 0, and then 1, 1, 1. And again, same way, right? Like Y1 is 2, there's no Y1 here, Y1 is 1, and Y1 is 1, which is how I got that. So to do composition with this kind of generalized format, I guess we'll call it, you can literally just do, and this is how you have to write it, S composed with T, is literally just the matrix S times the matrix T. And if you do out that multiplication, you're going to get this. And then as like a last step, that represents the complete composition here. And we just want the answers like in terms of like X's, basically. So we're going to do S, composed with T, this thing operating on X1, X2, because we started, that's where T starts, is like it's like a R2 vector. And then you can just take that matrix, so this matrix ST, right? And you can multiply it by X1, X2, and I'm going to put it over here. If you do that out, you would get this. And that'd be it. So this would be the, result of doing T on V and then S on T on V. But you can save yourself a lot of time in these kind of problems if you just write the matrix out, do the multiplication, then use that matrix operating on some arbitrary vector to get this. If you did it by actually doing out the substitution, basically you'd have to take this x as y1, and we'd pop it in there, and then this as y2, and we'd pop it in here and here and here, right? You can get an idea how messy that would be to do all of this plugged in, but actually, I guarantee you, I'm not going to do it because it's just tedious, but if you take all those things and you pop them in, you would get this. That's the result. But this is much quicker with just using matrices. All right, so I just wanted to mention these things. Don't really want to do any examples with them, but just to formalize the idea of an inverse transformation. We know it exists because we've been taking inverses from matrices, but so if S and T are linear transformations from Rn to Rn, so they have to be dimension preserving, right? Which makes sense if you think determinant. Okay. Then S and T are inverse transformations if these two things happen. So basically their compositions both equal the identity, right? It doesn't matter if you do T then S or S then T, you should get the n by n identity, right? And, that fits with our notion of A inverse A equals A inverse equals I n. This is basically the exact thing I'm talking about, but I'm using the notation of linear transformations. And then here, so T from Rn to Rn is invertible linear transformation. Then its standard matrix T is an invertible matrix, and this is saying that the standard matrix of the inverse is the inverse of the standard matrix, right? Which is kind of a funny thing to say, but basically, the way we found matrix inverses before is what we would use to find these kind of things that do this, right? So not super brilliant statements there, but I did want you to at least see these. So this is kind of the formalism for what an inverse transformation is.